Okay, good afternoon, everyone. So welcome to this afternoon's tutorial section. So our tutorial session is integrating large language models and knowledge graphs for next level artificial general AI. So I'm Shuri Pan from Griffith University. So together with some of other presenters, including Linghao Luo from Monash University, Kao Yang from Emory University, and also Jenny from Bosch. So we are going to give this exciting tutorial. So okay, so a little bit of introduction of the presenter today. So I'm Shuri Pan from Griffith University, and my research mainly focus on graph learning, graph machine learning, and also time series analysis, as well as large language model. And here we also have Linghao Luo. So Linghao Luo is the final year PhD student working in the area of knowledge graph as well as large language model and also their interaction. And today we are also have Professor Kao Yang here from the Emory University, and his research focus on data mining, knowledge graphs, and also the applications in healthcare. And today we also have some presenter from the industry. So we have Jenny here. Unfortunately, he couldn't get the visa, so he will present remotely via the Zoom later. And here's today's outline. So today, we will cover different aspects of this exciting area, including some general introduction of AGI, LLMs, and KGs, and also some of the challenges and opportunities in this interaction. And also Linghao Luo will cover some knowledge graph enhanced large language models, so including the KG enhanced LLM training, and also KG enhanced LLM reasoning, and also how can we build a unified KG and LLM reasoning models. And then we will have 30 minutes break. And then Professor Kao Yang will present the research on large language model enhanced knowledge graphs. So how can we leverage LLM to enhance the KG interaction or KG construction or compression, and how LLM can enhance the multimodality KGs. And then we will have Linghao to give some, we will have actually Jenny, who will give some application, real-world application from a very big company, Bosch, about the application of LM and KG, and then Linghao will give the final direction and conclusion. So let's get started. So the first part is about the introduction. So artificial general AI, I think is the ultimate goal of the AI community, right? And also now we have a lot of development in LLMs and also KGs. So, and also we will cover some limitations and opportunities towards AGI. So what is exactly AGI? So artificial general AI? Actually, there's no really well-defined definition here, but in general, so people believe that the AGI would be the AI system that had the human level general intelligence. So for the AGI system, it should be able to understand, learn, and reasoning, and also adapt to different scenarios, different applications, and different domains, and also can adapt over time. So that's the AGI. So the AGI is quite different from the current or existing or many past AI systems, which actually only have the specialized intelligence. For instance, AI system which can only play the chess or play the Go, or some AI systems which could do the face recognition, so especially focus on this face recognition, or even the autonomous driving car, and or some AI system which can help us to translate the language from English to Chinese or from Chinese to French. So this kind of specialized intelligence actually is not the AGI at this moment. And I think in our AI community, the ultimate goal is build the AGI. So right, so and everyone is very passionate about this, but this is very challenging, and we know that they are very challenging, and and there are different roles that may achieve the AGI. So people in this community think that there are different roles which can help us to achieve AGI. The first one would be the symbolisms. So here we believe that knowledge, the intelligence may emerge from some well-defined rules such as decision trees or some well-structured knowledge such as the knowledge graph or force or the logic. So by represent the knowledge in this way, so probably we will be able to build some AGI systems. For instance, in the past, so we got different kind of medical expert system, right? So which really depends on the doctors to summarize the rules to help them to make the diagnosis. Another role which may achieve the AGI would be the connectionism. So what's connectionism? Basically, it believes that the intelligence may emerge from the huge amount of connections, just like how our human brain works, right? So we have a huge amount of neuron, and then the emergence, the intelligence may emerge from this kind of connection and also activation. So here, so we got different kind of approach in under this branch. So we got the neural networks and also current deep learning techniques, right? So and also people believe that with more with more Unix, with more data, and then we can train a very big neural networks, such as this kind of ChatGPT or generative AI system, and eventually we may reach the AGI, right? And also some people believe that maybe the actionism would be the pathway to achieve the AGI. So what does that mean? It means that an AI system should be able to understand the world, right? And also should be able to receive the feedbacks from the environment, and we can also do some action, and then we get the feedback again, and so that the system can evolve. So typically these kind of systems are RL systems, right? So we can receive the reward and then we can evolve over time. So there are different roles to reach. People believe that that may achieve AGI, but currently some people also argue that maybe a single role is not good enough. We may need to combine some of these architectures. For instance, the neural symbolic, right? The LM and knowledge graph, and we are some of these folks. We believe that we should combine these kind of different approaches. So let's look at the AGI. So the connectionism, so which may lead to AGI. So currently the large language models hopefully is one of the most exciting innovations in AI in the last few years, right? So we got ChatGPT developing by OpenAI. We also have Gemini developed by Google, and recently, so in China, so there's a DeepSeek, right, developed by a small company, so which is really powerful. So actually, all these LMs are start with the transformer, which was developed in 2017, right? The attention is all unique. So start with that paper, and then you can see that over the years, there are many architecture about the language model have been developed, including, so in 2018, we got the BERT and also the origin of the GPT, this kind of GPT. And then in 2019, we got a T5 model and also GPT-2, and then 2020, we got GPT-3. And then in 2022, we know that the ChatGPT opened a new era. So where the conversational AI systems opens a lot of opportunities and for the whole world, right? So and then nowadays we got this kind of GPT-4o and right, and also Llama and DeepSeek, and in China there are also many other large language models such as Q1. So So, because LMs currently are really powerful, so we can see that we can use LM to do the translate the language from one to another, from English to French to China, and we can also use an LM to answer some very complicated questions, right? So for the QA answering, and also LM can be also used as an assistant for us to, for instance, to learn a new language, or to help us to do some conversations. And LM can also be used in solving very complicated math problems, right? So LM is really powerful nowadays. And but can LMs achieve AGI? I think this is still a debatable topic. And for instance, some of research, the local believe that LM wouldn't achieve AGI. He even discouraged the researcher doing more AGI, right? But why? Why is this the case? So because actually LLMs have many limitations. So here today, we will highlight some of these limitations. The first limitation, which is really widely known by many research, is the hallucination problems. So LM suffers the hallucination problem during reasoning. So here we provide some example. For instance, in the left, we ask a question: when did Einstein discover gravity? So LM may generate the answer like this: Einstein discovered the gravity in 1687. We know that it's not Einstein who discovered the gravity. It's Newton, right, who discovered the gravity. So this kind of answer, which is factually incorrect. So this is the problem of hallucination. And on the right-hand side, we also give another example. For instance, we know that LM is very powerful, so it can break a very complex question to a series steps, and then finally get the answer. This is called the train of thought, right? So for instance, we ask LM to do a little bit of mathematical proof of this problem, and LNT can, by using the train of thought, LNT can generate the reasoning path step by step. But if we check it carefully, actually these reasoning steps are not correct. This is also a type of hallucination. So, and also we know that another limitation of LM is that LM may have the problem of the may lack the up-to-date knowledge, basically. So sometimes you ask LM, it may return answer, I may need more information, sorry, I don't have the knowledge about this, right? So here's an example. For instance, we know that currently there's increased tense between China and also US about the tariff, right? And we can see that so Mr. Donald Trump actually changed his argument and also his action towards China on the tariff over 1 week. For instance, changes significantly from at the very beginning 10% to nowadays probably over 145. And for instance, if you ask this kind of question to LM, so because they are actually lack of the most up-to-date knowledge, and may not give you the correct answer. Some people may argue that, okay, nowadays LM may have access to the web, right? So you can search information. Now LM may not have this limitation, but actually even LM can access the net, as it may bring many other problems. For instance, how to access the reliability of the source, and also how do they incorporate this information into LM, right? So yes, another limitation is the lack of up-to-date knowledge. And also another limitation would be the interpretability. We know that to ensure the trustworthiness of AI, so interpretability is very important. We know that LM may generate some answer, or may generate some answer for you, but actually how LM represent the knowledge inside itself. LM is like a black box. We know that LM has billion scale of parameters, but which part of parameters are used for LM to generate the answer? So this is not known actually. So LM, from this perspective, LM It's like a black box. And also another limitation is that LLM is indecisive. So what does that mean? So we know that, so the principle of LLM is based on the next token prediction, right? So LLM will generate the sentence by token, and then, so for every token, so actually it's drawn from a distribution of the vocabulary, right? So because it draws from the distribution, so basically, if you ask LLM to generate the answer twice, so you may get different answers, right? So this is the indecisive problem, right? But in many domain, for instance, in the medical, in the legal domains, we may would like LM always generate the same answer with different times, right? So another limitation of LM is that LMs, yes, they are very powerful, but they're too heavy, right? They have so many parameters. It's really difficult to deploy LM to a very specific domain, right? So we probably don't have sufficient computational resources. So, and also, if for some domain, if you would like to train your LM, also requires a lot of data. So so it's very difficult to generalize the LM to a very specific domain. This is the another limitation. For instance, I got the data in my domain. So do I really need to train my own LLM, or can I just simply use or adapt existing LLM? This is really a difficult situation for many researchers. So LLMs are really powerful. Many people say that LLM just like the Superman of AI, right? So, but LLM are not perfect. There are a lot of limitations, and LLM probably is not the only way which can reach or the AGI, right? Who would be the watchman? So actually, I think I think we think that one of the possible answer would be the graphs. So especially the knowledge graphs. So why knowledge graphs? So we know that knowledge graphs is actually a structured data format or database which stores enormous facts in the way of triplets. So in the knowledge graph, we have a lot of triplets. And in the triplet, we have the head entity, the relation, the tail entities. And then we can construct this knowledge graph from the raw text, for instance, from the Wikipedia. And then we can see that this is the knowledge graph. Actually, inside this knowledge graph, there are a lot of triplets. For instance, the Barack Obama is the prediction of the United States. This is a triplet, including two entities and an edge. So the knowledge graph stores our real world knowledge in a structured manner. And with this knowledge graph, we can do a lot of downstream tasks, including the question answering and also the information retrieval. So why knowledge graphs may help us to achieve AGI? This is because knowledge graphs have a lot of advantages. First, the knowledge graphs are transparent. We mentioned that LLMs are black box, right? We don't know how the knowledge are represented in LLM. And when LLM do the reasoning, we don't know which part of parameters LLM used to derive the answer, right? But the knowledge graph itself is very transparent. So we know that the facts, right? So the ontologies, the facts are very transparent. After we construct the triplet from the raw text, we have the fixed and also transparent facts in the knowledge graph. We can leverage it. And when we use knowledge graph to do the reasoning, so actually we know that which fact we are using to derive the final answer. And also, knowledge graphs are dominant. We mentioned the LM is indecisive, right? But for the knowledge graph, so after we construct the knowledge graph, the fact is actually either a black or facts. So it won't change over time unless the information change, right? So otherwise it will remain very stable. So every time when you use the same knowledge graph, you will get the same result. But for LM, you use the same LM, you may get different answers. So knowledge graphs may help the AGI because knowledge graph also power the symbolic reasoning. Symbolic reasoning is very important and find many applications, especially if we try to answer some very complicated or complex queries. Here, for instance, here we have a question where the Canadian citizens with Turing Award generated. Actually, we can decompose this complex question to a couple of queries. For instance, we can first find who win the Turing Award, who is the Canada citizen, and then we take the intercept of their answer, and then we further execute another query. For instance, where are this person graduate from? So by this way, for instance, this is a symbolic reasoning. We can finally get the answer and answer really complex questions, right? Here we showed how we derive the final answer. For instance, for Turing Award, so we got a couple of persons, and also for the Canada citizen, we also have a couple of persons, and finally we know that Hinton and Benjo, right? And then we can find the graduate university, and then we can get the answer. So knowledge graph can help us to do the symbolic reasoning in a very effective way. So knowledge graph can also provide a lot of domain-specific knowledge. I think this is one of very important point here. So we know that LLM is data hungry. So if we would like to train a LLM for a very specific domain, we will need a lot of data, and also the parameters would be very huge, right? So how can we learn the new knowledge effectively? So probably we can use, we will discuss later, this kind of knowledge enhanced generation framework, right? So because in every single domain, we can construct their own knowledge graph. For instance, in the medical domain, we may construct a medical knowledge graph. In the legal domain, we may construct a legal knowledge graph. And then this domain-based knowledge graph provides sufficient knowledge or external knowledge which may help LLM to derive the correct answer, to overcome the hallucination problems. So, but actually, for the knowledge graph itself, there are also quite a few limitations. The first one is that knowledge graphs are actually quite difficult to construct. It requires a lot of data engineering work here. For instance, we may have different data source, and the data may be represented as table, web page, or images. And then we will require a knowledge acquisition steps, so which basically extract the entities, the relations from this kind of data. And finally, we get a raw knowledge graphs. And then this raw knowledge graph may be not perfect. We may need to further refine this knowledge graph to get a refined knowledge graph. And also when we have new entities, new facts, new data coming, so we got a existing knowledge graph. We would like to, for the new data, we need to do this process again to update from an existing knowledge graph to a refined knowledge graph. So knowledge graphs are quite difficult to construct. And also knowledge graphs are always incomplete to noise or quite noisy. This because we may use the NLP techniques, for instance, to do the entity recognition and also extract the relation. But not every technique is perfect, right? So we cannot get all the entities, all the correct relations. So the knowledge graph itself is not complete and always very noisy. So because knowledge graph itself is noisy. So when we do the downstream task, for instance, we do the embedding, so we may not get the correct answer. So, so here we summarize the pros and cons of LMs and knowledge graphs. And our position is that we may need to combine the two parts, LM and KGs, which may help us to further progress towards the AGI. So we know that for large language model, we know that they have a lot of general knowledge and also have very strong language processing capability and can be generalized to many domains, right? But LLM also suffers a lot of limitations. They have very implicit knowledge. We really don't know what is the knowledge represented inside the LM, and also LM suffers the problem of hallucination and also have the problem of indecisiveness, and their black box model, they lack domain-specific knowledge. So that's the LM. For the knowledge graphs, we know that, okay, they are structured knowledge, and also they are really accurate, right? After we shut the knowledge, they remain stable. So, and also it provides a lot of interpretability and also provide domain-specific knowledge, which may help us in many downstream applications, and also that we can always update the knowledge, and it's related easier than updating the LM or fine-tuning LM. But knowledge graph also have some limitations because they are always incomplete, and also knowledge graph just are just some triplets. They lack of the language processing capability and understanding, and also there will be always some unseen facts inside the knowledge graph. So since last year, we have been working on integrating large language models and knowledge graphs, and for instance, we represented a we released a roadmap last year, and I think this is a quite high cited paper, and now received nearly 1,000 citation. I think very close to that. I didn't check recently, but a lot of people now pay attention to this area. So actually inside this roadmap, we propose several methods that we can combine LM and KGs. For instance, we can leverage KG to enhance the reasoning capability of LMs. So because for any large language models, it takes as the input the text and also output the text, right? So during the LM training or reasoning step, we can inject the knowledge from the knowledge graph, because knowledge graph provides the structured facts and also domain-specific knowledge, and also can enhance the symbolic reasoning. So we inject the knowledge into the LM and eventually help to improve the reasoning capability of LMs. And on another side, LM actually can also enhance the knowledge graphs. For instance, if we would like to do a lot of KG-related tasks, including the KG construction, KG completion, so we have different KG tasks, and the focus of the KG Excel, right? But because LM has really strong language processing capability and also have a lot of general knowledge, LM can enhance this process. For instance, they can help us to recognize the entities, the relation between different knowledge graphs, and also provide a lot of other general ability to help us to finish different kind of KG tasks. And also, eventually, I think we may need to further integrate LM and KG. And here, in the first two approach here, so they focus only on a single part, but we may need to focus on both parts. For instance, LM may help us to enhance the KG, and KG may also help us to enhance the LLMs. So we would like to have a synergized LM and KGs. So if we have this kind of synergized model, actually we can apply to many applications. For instance, we got different data, right? So nowadays we got the text data, structured data, and even the image and video. For image, for instance, we still can construct some graph data there. So for this different kind of data, so we fit into some sort of synergized model. So this synergized model will integrate both the capability of LM and knowledge graphs. And then because we now got different modalities, so and also with large language models and also with graphs, we may need to further incorporate different kind of techniques. For instance, we would like to activate the LM's capability by prompt engineering, right? So for graph data, we may need to use graph neural networks, and also we always would like to do few short learning in context learning. And also, of course, presentation learning is very important. And because now we have the LM, so which is very good at neural reasoning, and we also have knowledge graph, so we may also would like to incorporate some neural symbolic reasoning techniques. So we got the synergized model as well as the techniques. Then we can apply to any downstream applications, including recommender assistance, AI assistance, dialogue systems, and search engines. That's our roadmap, and this was our vision last year, and we can see that there are quite a lot of applications since last few years, and for instance here one application about graph rack, so which basically use KGs to enhance the LM retrieval, and also so to enhance the RAG, the retrieval augmented generation process. So basically, so we got different data source. This data source can be structured or unstructured. We got a data pipeline to store or to transform this kind of data into knowledge graphs or into the vector database. So basically, we would like to have a graph database here. Of course, for the data, we would like to do the chunking, or we need to do the name entity recognition, and we need the embedding techniques to transform the original data to the graph data. And then from the user perspective, then they ask any question, right? And for any general AI applications, so these questions will search from the graph database. For instance, here we use Neo4j, right? And then during the process, we will return some context. And then with this context, and also original questions we fit into the LM, and then LM will return the answers to us, and then we further return the response to the user. So this is engineering pipeline of how can we integrate KG and LMs together. And also, for instance, KG and LM can be used in medical diagnosis. Again, so we may have some medical text, for instance, some medical report, and then of course at the very beginning we may need to store this kind of medical concept, for instance, into a database. And here we do the chunking. So we do the chunking, and then we do the entity extraction, relation extraction, and then we have a relation database and entity database. Eventually, we would like to construct a knowledge graphs. And then from the user perspective, right, the user may ask any clinical questions. Then we can use different framework to leverage the LM and KG. So for instance, we can develop some multi-agent framework which iteratively asks question of the LM, and if LM has sufficient knowledge to answer this question, then we'll return the answer. Otherwise, if we iteratively retrieve the relevant knowledge from the knowledge graph and finally return the answer. So there are a lot of applications here. And in the later, I think in the part 4, we will have and January here, we will present some real application from some big tech company, how they use the KG and LM together for some application. Okay, here's the first part, to show the introduction and background. So next we will have the Ling Hao, so who will give a introduction on the knowledge graph enhanced large language models. Thank you. Yeah.
Yeah. Thanks, Ray, for the great introduction about our goal about integrating large language model and knowledge graph toward artificial general intelligence. So in my part, I will give a presentation about how we can utilize the knowledge graph to enhance the large language model. So it can be combined with 3 ways. So we can utilize knowledge graph as a data source. So we can utilize the information from knowledge graph to help the large language model training, so we can get a better knowledge enhanced large language model. And also we can directly utilize the knowledge graph during the inference time of the large language model. Basically, we can directly inject the knowledge into the LM during the reasoning stage so that we do not need to conduct any training. So there will be more practical solution in the real world. And last, I will introduce like how we can combine the power of the knowledge graph and the LLM, so we can design a joint reasoning model that conduct reasoning with both the knowledge graph and the large language model. So we believe they can like pave the road, like combine the power of these two tools and to get a next step, artificial general intelligence. So like the first is like how we can utilize a knowledge graph to enhance the large language model training. So actually this kind of solution has been studied for actually quite a long time, even before the large language model. So the basic goal is like knowledge graph is a data. So we can get lots of data from the knowledge graph, and then we utilize it to train the large language model with its like pre-training or fine-tuning objects. So, but like what's the difference between the knowledge graph and the other data? So the knowledge graph actually is a structured data. So we need to somehow utilize this kind of structural information to generate the data that can be used for training. And the benefit of this data is like, for instance, in a knowledge graph, then a single triples, then it means like it's a single fact. So we can directly utilize this single facts to generate some training data, so we can tell the large language model like the latest knowledge about certain facts. But what if like we connect a path, we find a path, and we sample it from the knowledge graph? So this kind of structured information can be utilized for doing some like reasoning task. So basically it tells like how these facts are connected, so that rather than just tell what have been known in the knowledge graph, we can also teach large language model to conduct some reasoning based on like the connective of lots of different facts. Yep. So here is just a very simple solution. So we can just sample some triples from the knowledge graph, and we train the large language model with this kind of like triple level facts. So after training, the LM know like what kind of facts have been stored, then it can be utilized to do some fact prediction or hallucination detection. And also, in order to better capture the structural information of the knowledge graph, so sometimes the people will try to modify the architecture of the large language model. So somehow we need to better capture the structural information. So definitely we can directly like sample lots of paths from the knowledge graph, but it just sounds like very simple, like low order information. So for now, there are some like solution trying to utilize like the graph neural network and combine it with the transformer architecture of the large language model, so that it can better capture the structural knowledge of the knowledge graphs. Yeah. So recently, like there are some study like KG adapter. So basically, in order to better capture the structural information of the knowledge graph, so they will append additional components. Like here is like a well-designed KG adapter that can capture the structural information and knowledge graph, and it will combine with the transformer architecture, so that the LM can better capture the information from the knowledge graph and utilize this information to like doing some tasks like question answering or like doing some like communication with to solve some real world problems. Yeah, so they will, but this kind of techniques rather than just generate some data for model training or inject additional components, inject it to the large language model, they actually require retraining the weights of the LLM. But this actually is quite, for now, the LLM with maybe billions of parameters. So this kind of training require lots of resource, and it's not practical to adapt to the real world change. So like the example we have shown, like Donald Trump like make the decision on the tariffs change like even within a week. So it's impossible like to train a large language model in a daily period to adapt to this kind of real world changes. So we need some way to help the LM to better adapt to this kind of real world knowledge and we can like dynamically inject the latest knowledge into the LLM, so that we can always ask LLM about the real world knowledge rather than like training this kind of knowledge into the parameters of the LLM. So let's come actually to the second part, is like how we can utilize knowledge graph to enhance the LLM during the inference and the reasoning times. So in that way, basically we separate the knowledge and the LLM into two parts, and then we will inject this kind of knowledge into the LLM during the reasoning, and which is also being known as the retrieval augmented knowledge fusion. So they usually follows this kind of a retrieval then reasoning paradigm. Here we have the knowledge graph, we have a knowledge retriever, and we also have a separate large language model. Then given a user's question, we usually utilize our knowledge retrieval to retrieve knowledge from the knowledge graph. For instance, some triples that can represent certain factual knowledge. Then we inject this kind of retrieved knowledge into the context of the large language model, so that we can ask question, and given both the context and the question into the LLM, then the LLM can answer the question correctly, like which country is Obama from? We can retrieve some fact like Obama was born in Honolulu, and Honolulu was located in USA. So this kind of application are quite good because it can be parameter free. So for the knowledge retrieval, we can utilize like non-parameters based retrieval like BM25 or some other knowledge retrieval. And also for the LLM, we can easily utilize some black box LLM. So for example, ChatGPT, you cannot access to its parameters, so it will be hard to train it on your own data sets to inject the knowledge. So that this kind of like retrieval augmented knowledge fusion are widely applied in the application to inject the latest knowledge into the large language model. Yeah, even though this framework are very common, but there are some still challenge when we utilize the knowledge graph to enhance the LLM reasoning. So basically, the challenge comes to two parts. The first is like how we can effectively retrieve from the knowledge graphs. So the knowledge graph stores like billions of facts in a structured manner. Like given a user's question, how can we find the most relevant or useful facts from the knowledge graphs? There are definitely some solutions for right now, like entity linking or keyword-based search, or even based on embedding similarity. But there's still some limitation, like how to effectively utilize the structure of the knowledge graph to find the relevant information. And the second is like how we can enable LLM to reason on the retrieved knowledge structure. So well, definitely we can retrieve like some triples and represent it as a text. But this kind of way, if we utilize this kind of way to represent the knowledge, we might like remove the structure information between these facts. This kind of information can be quite crucial to conduct some complex reasoning tasks. But the LLM itself are not trained with this kind of structured knowledge. So they are inefficient in capture the structured information and to conduct the reasoning. So that's a true major challenge we want to address when we apply this kind of retrieval augmented knowledge fusion and utilize knowledge graph to enhance the large language model reasoning. Yeah, so to address this kind of like challenge, so we want to like first introduce one of our work called reasoning on graph, which has been accepted by ICLR 2024. And they try to address the two major questions like of the limitation of the large language model. And the first is the lack of up-to-date knowledge, and the second one is reasoning hallucination. So like the example we have shown, sometimes LLM might insufficient to access the latest knowledge, like what is the current like price of Apple, or what is the current tariff rate between China and the US. So this kind of information usually have been not stored in the LLM itself. And also when we ask LLM to conduct some reasoning tasks or complex reasoning tasks that require multi-hop of reasoning, then the reasoning process of the LLM might be incorrect. For example, like who is the brother of Justin Bieber? Then the LLM might say, okay, Justin Bieber is the child of Jeremy Bieber, who has a daughter named Alice Bieber. But and then the answer is like the brother of Justin Bieber is Alice Bieber. But this kind of reasoning process is incorrect, because we know that to find a brother of a certain person, then we need to find like the father of this person, and also this person maybe have a son. So this kind of reasoning hallucination also deteriorates the performance of the large language model and also the trustworthiness of it. So like the question we just proposed, like how we can conduct the reasoning on graph. So in here, basically, we try to follow the paradigm called plan and solve reasoning. So like a human, when we usually face a complex question, we usually come up with a plan. Then we can conduct our reasoning that follows this kind of plan. For example, like who is a child of Alice? Then we can generate a plan. Like the first step is to find the person that Alice is married to. Then in the second step, then we find the child of that person. Based on this plan, we can conduct the reasoning step by step. So Alice is married to Bob, and Bob is the father of Charlie, so that the final answer is Charlie. So this kind of plan and solve reasoning are commonly used to enhance the reasoning ability of the large language model. But how can we apply this paradigm to the knowledge graphs is what we have proposed in this paper. So in here, we try to utilize the relation paths of the knowledge graph as the plans. So the knowledge graph contains lots of triples and also lots of relations. So the relation path actually is a sequence of relations that can be served as a faithful plan for reasoning on graphs. So still take the same example, who is a child of Alice? Then in order to answer this question, we can find a relation path. So the first step is married to, and the second step is father of. So these plans express the semantic like finding the person that Alice is married to and find the child of that person. So we can execute this plan on the graphs to find a final reasoning path. Like basically we place the entity into the relation path and get a final reasoning path. So Alice is married to Bob, and Bob is the father of Charlie. So definitely the Charlie is the final answer. Yeah, so here is the overall framework of our reasoning on graph. So we call it like planning, retrieval, and reasoning. So given the question like who is the nationality of Joe Biden, we first ask the large language model to generate some relation paths as faithful plan. So for example, we can generate plan like a born in and a city of, and also the graduate from, located in. So based on this kind of generated relation path, we can apply it to the knowledge graph. So basically, we can follow this kind of relation path to do some searching. For example, we can use a constraint breadth search. So we can find lots of reasoning paths from the knowledge graph. For example, Joe Biden was born in Scrutinization, and Scrutinization is a city of USA. So after we collect this kind of reasoning paths from the knowledge graph, we will feed it into the context of the large language model to conduct the reasoning. So please answer the question based on the reasoning. And based on this kind of retrieved reasoning path, we can also not only generate the final answer correctly, we can also provide the explanation to the users. Yeah, it sounds very, very promising solution, but how can we achieve it? The large language model itself has zero knowledge about the knowledge graph. If we have, then we don't need a knowledge graph, right? So how can we make sure the LM can generate the faithful relation path as a plan? And how can, after we retrieve the reasoning path, how can we ask LM to conduct the reasoning on the retrieved results? So that's the two challenges we are facing right now. So here is the object of our model. So given the question, we first ask LM to generate a plan Z here. And based on the plan, and we execute it on the graph G, we can generate the final answer. So the problem is like we do not know what is the good plan, what is the golden plan on the knowledge graph that can lead us to generate the final answer. So in order to achieve this, we try to optimize the evidence lower bound of these objects. So we decompose it into two object functions. So the first one is called planning optimization. So we have like estimated posterior distribution of the golden plan, and we want to make sure the large language model can generate this plan correctly. So we minimize the KL divergences. And also based on the plan, we want to ask LLM to generate the final question correctly so that you can know how to reason on the structural knowledge we provided to it. Yeah. So the first object is planning optimization. So basically, we try to distill the relation information from the knowledge graph into the large language model so that it can generate like a truthful, faithful relation path as planned. So it will generate the like the relation that actually exists in the knowledge graphs. And in order to estimate the posterior distribution of this faithful path, faithful plans, we actually utilize the shortest path connected the question and answer in our training data and in the knowledge graphs. So we estimate the posterior distribution with this kind of, with the distribution of the shortest path, so that we can minimize the KL divergency between the posterior distribution and also the plans generated by the large language model. So here, basically, we have a set of plans. We have a set of like shortest path as a faithful plan, and we want the large language model, given the question, to generate these plans correctly. So that is the planning optimization. And for the reasoning optimization, basically, we try to enable the large language model to conduct reasoning based on the retrieve plans. So we feed the retrieve reasoning path and the question into the large language model, and we ask LM to maximize its probability of generating final answer correctly, so that this kind of complex planning, retrieval, and reasoning framework can be decomposed into two simple instruction turning tasks. So the first one is to, given the question, generate the plans correctly. And the second one is, given the final reasoning path and the question, generates the answer correctly. So our model are simultaneously trained with these two objects, and we just utilize two prompts to do the supervised fine tuning. Yeah. So the result actually quite interesting. So definitely we can compare the performance with lots of KGQA benchmark data set. We can compare with simple like graph reasoning based method that purely conduct the reasoning on the graph. And also we have some retrieval based mechanism which retrieve the information from knowledge graph. And also we have some large language model that purely based on its internal knowledge to do the question answering. So we can see that our method significantly improved the performance against the existing method in both like the HIT1 and F1. And also our model basically can do two things. The first one is do the planning, and the second one is to do the reasoning. So can we just simply utilize the planning module of our method? Because in our experiments, we just trained a 7 billion model, which is quite small compared to the existing large language model, maybe with 100 billion of parameters. So we test another experiment setting is like, we just use our model as a planner. So we generate some plan and get the reasoning path. And after that, we feed this reasoning path into a more powerful large language model to see if we can get a better performance. So from result here, we can see that our method can be plug and play with other large language model to get a very good performance improvements. Instead of just the result, we also try to provide some explanation. That is the thing that very crucial right now in the application of applying large language model. So we don't just want to know the final answer, but we also want to know how can we achieve this final answer. So the reasoning process if we can provide this kind of explanation for its reasoning result, it can be quite helpful to tell the people to trust the result and also verify the result of the LM. So in here, we can see that our method can actually generate, based on the path we provided, the LM can generate explainable results, and it can help the user to understand why this answer has been achieved, and also you can reduce the hallucination and also provide update to knowledge of the large language model. Yeah. So yeah, from this paper, we can see by incorporating the knowledge graph with the large language model, we can provide like some interpretable reasoning process and also a very good performance. But there are still some limitations because in the end, we ask the LM to do the final reasoning and the generation. Even though we can provide LLM with this kind of context information, such as reasoning path. The LLM might not follow what have been given to him. It still can do some hallucination. And also we utilize LLM to do the planning. And we found that sometimes even with this kind of planning optimization, the LLM can still have hallucination. So it will hallucinate some non-exist relation and non-exist path. So simple, this kind of simple knowledge graph enhanced reasoning like ROG paradigm cannot still achieve 100% faithful reasoning during like the generation of the LLM is not controlled by us. And so we have do some analysis. We found that there are only like 67% of the paths generated by the ROG are actually correct. So there are lots of hallucination issues we need to address. And the reason is like the LLM are not controlled. They're just doing some like freestyle generation. So in order to eliminate this kind of hallucination, we introduce the graph constraint reasoning. So we utilize the graph structure as the constraint of the LLM generation step so that it can generate the reasoning path correctly. And here is just like how we get like inspiration from this. So for the conventional like chain of thought reasoning, so the LLM will generate the reasoning process token by token. Then you will start from the certain question that end at the final answer. So the whole reasoning process actually conducted in the parameter space of the large language model. So sometimes it's reasonable if some facts that do not exist. And also in the graph reasoning domain, so for now, there are lots of like agent-based method. So basically, we ask LM as a iterative agent. So we start from the certain entity on the graph, for example, USA. Then it will based on the structure, and it will select the most possible like entity for the next steps. So like for the USA, the next step might be like the ex-president of USA is Barack Obama. Then the spouse of Barack Obama is Michelle Obama. So that the LM will follow the structure on the knowledge graph to find the path leads to the final answer. So these are like some agent-based mechanisms are also quite popular in nowadays. But the limitation of this paradigm is like it actually requires iterative interaction with the knowledge graph. So for example, for a two-hop question, you at least require 2 times of interaction between the knowledge graph and the large language model. So that leads to lots of like token consumption and also like the inference time. And we try to like combine this kind of 2 technique together. So can we ask LM to do the reasoning, but with their like internal knowledge and also with the parameters, and also with some kind of constraint from the knowledge graphs. So here we present graph constraint reasoning. So given the question, we build a knowledge graph tree, and this is like we convert the graph structure into a prefix tree. Then we utilize it to constrain the decoding process of the LM. So we convert a graph into a tree-like structure. Then the LM during the generation will only generate the tokens that have been verified by our constraint. So in that way, we can easily combine the structural knowledge and also the neural, like the parameter of the LM to conduct the reasoning. So like is how we convert the graph into a constraint. So we utilize the prefix tree. So basically, the prefix tree is like a structure to store a set of string, then where each node is actually a common prefix of its children. So it's ideally to represent a knowledge graph because like if we try to find a path, then lots of paths might share like a common prefix. So that is ideal choice for encoding the reasoning path for knowledge graph and utilize for LLM to efficiently traverse on the graph structures. So given a graph, basically we can utilize some like a path searching algorithm, like breadth first search, deep first search, or random walk to get a lot of set of candidates paths that represent the original structure of the knowledge graphs. Then we can feed them as some kind of strings. So we can utilize the tokenizer to tokenize into lots of tokens, and then we can build a tree structures here. So start from the beginning of the sentence, then we can have like USA and also the relation capital of Washington, DC, and end of the string. So basically, based on each path on the tree, we just like traverse a single path in the knowledge graphs. So that by applying this kind of structure to the decoding process of the LLM, the LLM can easily traverse the path on the knowledge graphs, but without like iteratively interact with the knowledge graph structure. You can just like doing the generation, then during the generation, basically it's doing the traversal on graphs. And it will be very efficient, and it will not like require like the iterative interactions. Yeah, so here is like how we do it. So we can see that given like basically we do not need to modify the decoding process of the LLM. So during the decoding stage, so like originally the LLM can select the next tokens based on its vocabulary dictionary. So it can select any word it want to generate. But in here we apply the constraint with our prefix tree, so that LLM can only generate the tokens that have been like verified in the tree. So that after the generation, after graph constraint decoding, it will generate like a faithful path that exists in the knowledge graphs. Then after that, we will switch back to the original decoding. So we already got the path, we will finish the reasoning process. Then what is the final answer? So that we can just utilize the internal knowledge of the LLM, internal reasoning ability to decode the final answer. So here we can see that basically in here we not inject the knowledge into the input of the LLM. We just put a constraint in the decoding process, so that we don't need to modify the LLM itself. And also it can be combined with lots of advanced decoding mechanisms. For example, Bing search. We can simultaneously search like maybe 10 paths together and combine this kind of result to generate the final answer. And also there are some like Monte Carlo search. So this kind of technique can both be integrated in this framework to enable like a better reasoning performance. So the result also quite good. So I think also we compare with our previous reasoning on graph, we also get a very good performance improvement. And another good thing is like this kind of strategy are very efficient, because like for the conventional retrieval-based mechanism, definitely they are very efficient because they only do the embedding offline. Then in the online retrieval, they just calculate the embedding similarity. That will be very quick. But like the limitation is this kind of embedding-based method fail to consider the structure of the knowledge graph, so they lead to a suboptimal performance. And also there are some agent-based methods, like I just discussed, like iteratively interact with the knowledge graph. So even though their performance are quite good, but this require lots of large language model cores, and also the cost of lots of LM tokens. So our method actually retrieve a very good balance between the performance and also the speed, because we do not need to like inject knowledge into the prompt. So we have zero additional token consumptions. It's just like the question itself. And also the good things, like because we apply the constraint into the LM reasoning process, so it can always generate the paths that have been verified in the knowledge graph. So we can eliminate the hallucination issue. So you can see here, if we remove the constraint, then they are like around like 40% hallucinated reasoning paths. So that is not the desired result we want to have. We want not only the result is correct, we also want the reasoning process is correct. And this and also an interesting finding is here in the CWQ dataset. Sometimes we remove the constraint, even though the performance are also slightly higher, but we also observe like 50% hallucination. So that shows that sometimes LM can generate the answer correctly, but the reasoning process are totally incorrect. So this is also not desired in the real world applications. But with our constraint decoding, we can make sure the whole reasoning process is verifiable and also trustful. Yeah, so that's our second attempt about how we apply the knowledge graph to enhance the LLM reasoning to achieve like faithful and interpretable results. But even though this paradigm seems very like well defined, also widely applied in the real application, there are still some challenge we need to address. The first is we need to like get information from the knowledge graphs. But we all know that the knowledge graphs are very, very difficult to construct it. And also there are some incomplete information in the knowledge graphs. So if we directly retrieve, for example, a path from knowledge graph, but what if the knowledge graphs are incomplete? We cannot find the path. But in that case, maybe we cannot get the final answer from the knowledge graph. And also this kind of construction from the raw documents can also lead to some information losses. So we convert the raw document into a knowledge graph, then maybe some factual knowledge has been ignored and have not been properly represented in the knowledge graph. So this kind of directly utilize knowledge graph to enhance the reasoning have a certain limitation. So we are thinking about, can we combine the knowledge graph, original documents, and also the large language model? Can we utilize this kind of like three information together to get a better performance? And also, can we, even though the knowledge graph itself are incomplete, can we conduct some reasoning on the knowledge graph so that we can maybe somehow like predict the missing facts and also get new information that can be utilized for LLM reasoning? So one of the recent trending topic is called graph enhanced RAG. So basically, given a set of raw documents, we will build a graph structure. Like we will utilize a graph structure to explicitly model the relation between the documents. So it can allow more effective and efficient retrieval based on it. But lots of existing like graph enhanced RAG utilize the existing like a relationship. Like for example, for a citation network, there are some like reference relation between the documents, and also like for example in the Wikipedia, there are some hyperlinks between the documents. But this kind of information are only provided the cross relationship that are not like actually capture the factual level information in different corpus. So that even though we can utilize the graph structure to find the relevant documents and put the document into the LM to answer the question correctly, but this kind of like graph structure are not good enough to, and also we do not utilize like some reasoning mechanism to, for example, for a multi-hop question, they require maybe multiple different connected documents. So that how can we do this? It is the thing we want to study in this work. So we try to unify the ability of the graph reasoning and also the large language model reasoning to get like the next level artificial general intelligence. So in here, instead of use the existing relationship, we try to utilize the knowledge graphs as a structured index of knowledge across different documents. So for example, given a set of raw documents, for example, like Barack Obama and the city is born, and also some information about Michelle Obama. So it can be like separate Wikipedia pages. So we can extract the triples from this kind of documents and construct I construct a knowledge graph. So in this knowledge graph, different knowledge in different documents are actually densely connected in a local structure. So this kind of structure can well represent the knowledge across different documents and enable accurate retrieval and reasoning. So the problem is like how we can utilize this kind of structure and conduct the reasoning on the graph part and give the information to the large language model to enhance its reasoning ability. One way of doing that is utilize graph neural networks. So graph neural network has demonstrated impressive performance in the graph rack due to its powerful graph reasoning ability. So it can, like for example, reason on the graph structure and to predict some like possible answer or possible like, or you can like predict like a subgraph structure that can be returned to the large language model. For example, in the GNRAG, so given the question, it will fit it into a retriever powered by the graph neural networks. So start from some certain question entity, it will utilize graph neural network to conduct the message passing on the graph structure so that it will directly predict the possible answer. So in here, it's just like reasoning only on the graph space. So even though sometimes the answer and the question are not directly connected, maybe there are some hidden paths in the graph structure that can be utilized to deduct the final answer. And also you will combine the information like some, for example, some relation paths or some reasoning generated by the LLM. So you will, in the final reasoning, basically you combine the information provided after the graph reasoning and also the LLM itself to generate the final answer. Even though this kind of thing, this kind of paradigm will integrate the graph reasoning and LLM reasoning in a unified framework, but it still have a certain limitation attribute from stem from the graph neural networks. So for now, lots of graph neural network actually need to like training from the scratch on a new data sets. There are no like a foundation model in the graph domain that can be trained on certain data sets and directly applied to unseen data sets. So this limited the applicability of this kind of like GN RAG. We do not want to like training the model from scratch on a new data set is given. We just want to directly like the LLM, given a new data set, we can do the retrieval, we can do the graph reasoning and LLM reasoning. So in order to address this limitation, we actually propose the first graph foundation model for LLM retrieval augmented generation. So in this framework, we present the first graph foundation model retriever that actually combines the graph reasoning with the LLM reasoning, and we combine the two techniques together to enable a better retrieval augmented generation. So basically, we design a graph foundation model. A foundation model also is powered by a graph neural network, and it has been trained on over like 60 different knowledge graph with 40 million triples. And after this kind of like large amount of training, we have open source a 8 million parameters model that can be directly applied to a new unseen knowledge graph and directly conduct the retrieval and the reasoning. So you can see here, given a set of documents, we will convert it into a knowledge graph. And given the question and the knowledge graph, we feed them into a freeze graph foundation model retriever. Then we can retrieve some lots so we conduct the reasoning on the graph and retrieve some relevant document and feed it with a question into the LLM. So that you can see both the graph foundation model and also the LLM are freeze in this stage. So it can be directly applied to an unseen knowledge graph to conduct the reasoning. So here is the overall architecture of our method. So given the question, we first utilize some sentence embedding model to convert into a certain question embedding. And this embedding, and for all the entities on the graph, we will only initialize the embedding that have the entity that mentioned in the question. For example, Barack Obama is a politician of which country? Then given the knowledge graph, we only initialize the embedding of Barack Obama with the query embedding. And for the other one, we will initialize with 0. So after that, we can conduct a query dependent message passing. So basically, we will propagate the information from the question entity to all the other entity on the graphs so that we can capture their relevance to the certain questions. So after like multi-stack layers of message passing, basically we can capture like the multi-hop information in the knowledge graph and find the potential reasoning paths that lead to the final answer. So after that, we can get the probability of the entity score. Then this kind of score measures how relevant the certain entity to the question. For example, in here, like USA, it has the highest probability because it can directly answer the questions. So based on this probability, we will map it back to the original document. So here we have an entity to document inverted index. So basically, it's like an entity can be mentioned simultaneously in multiple different documents. So we can utilize this relevant scores and the inverted index to find the relevant document and feed it together with the question into the LLM to generate the final answer. So in here, we can see we have graph foundation model and focusing on the graph reasoning part, and the large language model focusing on its reasoning. So you can, based on the retrieved knowledge, and conduct the reasoning. And in order to solve the graph construction, like the bottleneck, we directly utilize the large language model to generate the knowledge graphs. So we utilize GPT-4o and with some like one-shot prompt to extract the knowledge graph from documents, and also some embedding-based model to do the entity resolution. So it's just like a very simple solution here. It can definitely be replaced with like more advanced graph construction pipelines. And the training of our foundation model basically is to predict the target entity given a query. So after like multi-layer of GM message passing, we can get the embedding, or can get the probability of all the entities in the graphs. Basically, it measures how important is to the certain query. So in our object function, basically, given a query, we want to maximize the probability of the target entities. So in the training, we have also conduct like two-stage training. So the first stage, like we have lots of knowledge graph, but we don't have lots of like query and answer pairs. How can we like generate some data from the knowledge graph to do the training? So one way is like for each triples in the knowledge graph, like what we have discussed in the first paper, like in the first section, like we generate some data from the knowledge graph to enhance the model training. So we sample lots of triples, and for example, Barack Obama was born in Honolulu. Then we simply mask out the tail entity. So we can generate lots of pseudo query or synthetic query, like Barack Obama born in, then we try to predict the tail. So it's just like synthetic query that can be utilized to initiate the parameters of our foundation model. Then after the self-supervised training, we can utilize our label data. So we have the real-world natural language question and also some supporting documents, and we can extract the entity from supporting document. So we try to ask our foundation model to predict this kind of like target entity and conduct the reasoning on the graphs. So here is just some experiment results. So basically, the training is not very time consuming. And also we train on like our 60 knowledge graph with like 40 million triples. So after this kind of pre-training and fine-tuning, our model had a very good performance in both graph reasoning and question answering. So here you can see when we compare with some naive like single-step method, so you directly retrieve the documents without considering the graph structure, our method significantly outperforms the existing ones. And also there are some graph-based retrieval mechanism like LagRag or HippoRag. They are based on the graph structure, but they are not powered by some graph foundation model. So they have like suboptimal performance on conducting the graph reasoning and find the relevant documents. Yeah, so and also our method can be like outperform some like multi-step iterative method. So the LM will, based on the retrieval result, and do the retrieve again and again until it finds the final answer. So this kind of like iterative pipeline also require lots of LM cores and also lots of token cost. But our method, because the message passing can be stacked multiple layer, basically in a single step, we already capture like the multi-hop information on the graphs, so that you can directly find the final answer with a single LM, with a single message passing forward. So, and also our method can be, in order to better combine the graph reasoning and the LM reasoning, our method can be combined with some like agent-based framework. So as shown in this figure. So here this framework powered by two components. So first one is our GFM retriever. Then it will retrieve some document and feed it into the LM. Then the LM can decide whether there are enough information to answer the question. So if it's not, it will identify some new starting entity and feed it back to our graph foundation model to do the retrieve again. So here we can see we have both, we can iteratively combine the graph reasoning and also the LM reasoning until it finds the final answer. So you can see by combining this kind of iterative framework, our performance are even better than the previous single step method. So basically we joined reasoning on the graphs with the large language models. Yeah, and here is just some efficiency because basically we conduct the reasoning with graph neural networks and with only like single LM inference so that we have better we have more less time consumption compared to the previous like agent-based method. And some of them may have the question like how the graph neural network conducts multi-hop reasoning on the graph structure by stacking multiple layers. So basically, this kind of information can be like provided to the path can utilized by the graph neural network to conduct the reasoning can actually be shown to provide the interpretability of our model. So basically, because we stack multiple different layers, then we can calculate the partial derivatives of the triples at each layer with respect to the final prediction. And after that, we can utilize a bin search to find the paths on the graphs. So that it means that these paths are identified by the graph neural network that can be utilized to support the reasoning. So here you can see that, given the question, what is the football club owned by the singer of this song? Then we can find the top two paths like this song was sung by Elton John, and Elton John has a football club named after him. So basically, we can provide the interpretation results to the user, so we can our reasoning on graphs. The process of reasoning on graph actually is explicit to the user, so it's not like a black box like large language model. And the last thing is the zero-shot generability. So because we claim our model as a foundation model, then we definitely need to test the performance on a new data set, new domains without training it. So we test the performance on 7 domain-specific like data set, like for example, biomedical, customer support, also general knowledge. So our method also like outperforms existing graph-based method. So it shows like it's zero-shot transferability to new data sets. And the performance can also be keep improving with some simple fine-tuning. So it highlights its ability, like transferability as a foundation model. And another good property of the foundation model is called narrow scaling law. So the model performance will tend to increase with the size of training data and the model parameter size. So also we observe the same property in our method. So by increase both the parameter size from 0.0 billion to 8 million, and also training data from 3,000 to like around 50,000, we can see the performance both increase. So this highlights with more training data and more like model parameters, we can finally derive the final graph foundation model that get a better performance and a better generability across different data sets. Yeah, so that's a summary of this section. So in this section, we're talking about how to utilize the knowledge graph to enhance the large language model. So there are 3 ways to do it. First is like we can utilize the data from the knowledge graph to enhance LM training. And also we can utilize knowledge graph to directly utilize knowledge graph into the reasoning and inference stage of the LM. And we present 2 papers that following this paradigm. And the last is like we're trying to unify the graph reasoning and LM reasoning in a unified framework and design like a foundation model that combine the power of this knowledge graph and the large language model together and to achieve like a better performance and maybe pave the road for the next level general artificial intelligence. So I think that's it for this part. So I think we still have some time. Do we have any like questions from the audience?
And there is a problem in terms of the generalization capabilities of this model because it is not possible to generalize to unobserved facts in the knowledge graph. So the question is about if it is possible to infer new facts in real time, for instance.
Yeah, that is a very good question. So I think the question is like, instead of like predicting the existing, instead of using it for retrieval, can we utilize, maybe apply to the knowledge graph to predict like some unseen facts? So we can, basically it's a knowledge graph completion task. So I think for now we haven't tested yet, but I think it definitely can, because in the training objects, the first training object basically is a knowledge graph completion object. So given head entity and relation, we try to predict the tail. So in here, we're just focusing on the second part. We try to predict the target entity, but it definitely can be utilized so to conduct some like knowledge graph completion task. Yeah, so I think as a foundation model, definitely it should exhibit the ability in across different tasks. So I think knowledge graph completion definitely is one way we can explore. Thank you for the question.
Thank you for the talk. That's very nice. So more of the work looks like kind of retrieval based. What if when we think of knowledge graphs, we can perform complex queries like that has complex operation count, filter out, and so on. So here it looks like a kind of identifying a single fact. So when it's smelt up, it's a kind of chain of identifying evidences. So how can we adapt your model to apply those questions that need more complex operations?
Yeah, that's a very good question. So I think the question is like, how can we combine our model to conduct some complex reasoning, like maybe require some logical operation and also some like numerical operations on the knowledge graph to get a better performance. Yeah, I think that's a very good question. For now, we just focusing on some multi-hop question. So basically, it's just fact related. I think your question is more like require some logical operation. So I think one way to do it, so for example, if we consider our ROG paper, in here, we just utilize the relation path as the plans. But also in order to conduct this kind of numerical operation, one way we usually we do is to generate some first order logic, right? So we can execute this logic on the knowledge graph to get the result. So if we replace the concept of plans to another way, if we try to address the like complex logical question, then the plan itself can be some logical operation. For example, like a semantic query in the knowledge graph. So we can execute this logical query on some knowledge graph engine to get to calculate the result and provide it back to the large language model. I think in the end we have like some future study to show that how can we combine the the symbolic reasoning of the knowledge graph with LM, and it can better solve this kind of problem. I think if your search the name is called like KAG, it's a very good framework published by like the Ant group. So they actually in their framework they try to address your problem. They combine the logical reasoning with the LM reasoning. So they're focusing on the part that you are studying. Your questions. So I think maybe yeah, you can maybe if you are very eager to know, you can search the name, but also you can wait for the end of this tutorial to have some idea about it. Yeah, thanks.
How sensitive is it to similar names? Like, for example, I see father of over here, but if it's dad of, will the search fail, for example? Is it sensitive to synonyms? For example, you could create a knowledge graph, but the edges could be labeled slightly different. And maybe you write a cipher query and it uses a different kind of vocabulary, and would that be handled through some of the work that you have done?
Well, I think the question is like when you have different query or different knowledge graph.
You have a query, but it is expressed in a slightly different vocabulary. For example, father of, it could be written as dad of.
Yeah, that's a good question. So there are two ways to solve this problem. So for example, in the ROG, basically we distilled. So there are two things like there are questions in the natural language question asked by the user, and also the relation stored in the knowledge graphs. So like previously we will do some like semantic matching or relation linking to find like some similar information. But in here, we try to utilize large language model to bridge this gap. So the large language model for in here basically do the planning. It will somehow handle this problem. It will understand the intent, understand the question, semantic of the user's question, and only generated the relations that are valid in the knowledge graphs, so that you can somehow like link this kind of similar semantic information. And even though the user asks like the dad of who is the dad of, but we know that in our knowledge graph there is a father of stored in the knowledge graph, then we will only generate the father of. And I think this technique called like semantic align with the schema. So we try to make sure the generation align with the schema we defined in the knowledge graph. And instead of simple training, there are also other way to do it. For example, just provided the relation in the context. Yeah, thanks for the question. Okay, I think if no more questions, then we can have a coffee break and we will be back in 3:30. Thank you everyone for attending.
Thank you.
Yeah, maybe you can tell me like the five it's kind of like how they got to
还有呢？700块的房子。700块。都说了吗？你能听懂这个？我们听不懂这个，快。我这边电脑其他语。我手机台太好了。这样吧。没有在干嘛？这样。真的。我在想你本来看你这人家没有，就是人家就把人一方面。
对的名字。
是吧
他好像不在。
？OK，如果在的话，你就叫他 unmute 一下，看看能不能，你在这呗，等着呗。
好像不在。老师，我这个 slide 是飞线的这样子。方老师问你
哪个方案是？
方圆，
对呀，
那其他的那个不是很熟的
啊？
其他不是很熟的呢？
对呀，
有些任务然后一个不知道哪个不是什么，
哎呀，
印度的可以的。
嗯，
Okay, okay. No, I don't know. Where do we get the part of the right?
난장.
我觉得我要站旁边一点，不是免得被那个光照着，有点搞笑。被那个光照着就很搞笑。
一直照着眼睛。
对，脸上还有字。行。人来讲。Okay, so yeah, we are about the time. So yeah, let's get started. So I'm Carl Yang from Emory University, and I'm very pleased to continue this tutorial on part 3, language model, how language model can help constructing or basically improving existing knowledge graphs. So thanks to Shi and Ling Hao, I guess you guys have a good idea, a pretty good idea of why we need to do this, right? So you know, like knowledge graphs in the real world, like one of the very important limitation is you never get as much coverage as what you get from large language models, right? Because those models are trained on really large data. But knowledge graphs, even you have like a few millions of nodes, which are like a pretty large knowledge graphs nowadays, right? But this amount of data, or the data you actually used to construct these knowledge graphs, are much like smaller than what we use to like train large language models, right? So the coverage is a very important limitation of a knowledge graph. And in the same time, we want the knowledge to in the graph to be pretty accurate, right? Otherwise, there's not a lot of meaning to really do this kind of graph supported RAG or graph supported reasoning compared with what you can do in the original raw text you can find on the web, right? So accuracy or quality is still very important. So the main thing I want to talk about today is how we can, like, what are some important directions we can work on, or what are the things we should pay attention to when we improve, when we try to so-called improve the knowledge graph, right? So basically we want to improve the coverage but still maintain relatively good quality of the knowledge. So here is a picture I actually got from one of the papers we recently wrote, and in the middle part is actually the point we are going to talk about in the first direction, where we use language models to improve the knowledge graph by integrating KGs you got from different resources, you got from different platforms or built by different people, right? So the middle part, you can see there are basically multiple kind of knowledge graphs, or sets of concepts you can get from EHR data, you can get from some particular existing existing knowledge graphs, right? In the middle is more like a ontology, where you get this tree hierarchical kind of structure of some diseases or other types of things, right? On the right is more like our traditional understanding of a knowledge graph, where you get different types of entities, and they are like connected by different types of relations, right? And there are also just some sets of entities you can get from like a table or some kind of patient data, right? You basically get this kind of individual like entities too. So yeah, this whole example is in the biomedical domain, because like in my own research, we kind of put all of the efforts into all of these techniques, their applications actually in the medical, biomedical, or healthcare like domain. So many of the things you see I talk about is about has like examples from like healthcare. But these techniques, they are I think fundamentally they are general. They are generalizable to like other domains data as well. So on the left and the right side actually are more like the examples I will be talking about in the next two kind of directions, other than integrating knowledge graphs. This is more like how you extract like more entities relations hopefully using large language models, right? From like other kinds of literature, from all of the new research people have been doing, publishing on the web, right? So you can use this knowledge to improve the like your existing knowledge graph. And on the other side is we go beyond the text. We take we look at other modalities of data, patient data like tabular data, like ECG, EEG, this kind of time series physiological waveform data, and imaging data, different kind of CT scans, MRI scans, and like assessment surveys you do, like basically take take the records of what you do outside the hospital, right? So these are, again, like a healthcare kind of scenario, but you can imagine in your other scenarios, you have legal document, right? You have some financial like guidelines, right? These things you can also use to basically extract entities, build your knowledge graph, improve your knowledge graph. So I will be basically introducing some of the works I think are pretty like typical in each of the directions I'm going to talk about. Of course, we are going to promote our own work and some of this like which I know more details of, right? So hopefully as a tutorial, I can really like give you the right kind of right description of the work, right? If those are our own work. There are some like works of the other groups I try to understand, and I will also like try to give you like let you know what I understood from the work, but they are not 100% like guaranteed to be correct. Okay, so this is the work actually we did. So hopefully my understanding is more of accurate. So the problem is we have like we do the knowledge graph integration, right? So basically you have like two knowledge graphs, or like one of the knowledge graph, the other more like of an ontology kind of structure. So using ontology is because we usually for some of the entity alignment or entity focused kind of studies, right? The entities are often organized in an ontology or a hierarchy, right? Because like in the real world, if you think about concepts, right, you seldomly have you seldomly model them as just a free set, right? Usually you have different for example, diseases here, right? The diseases, they form some kind of a hierarchy. And usually like at least in medical domain, as I know, people have already spent a lot of effort to arrange things in a hierarchy, in a hierarchical way as they could, right? So we started from there. Like if you have a knowledge graph, like from some certain, like if someone built a knowledge graph, let's say particular for diabetes or for some particular disease, for some particular like kind of conditions, right? You can also like you can also basically try to put this knowledge graph like align it with the like existing ontology, right? That is a problem. So right, actually there was an audience who asked about why basically give us more motivation to do this is you basically in different domains you use different words to describe the same things, right? And in medical domain you have disease code, and this coding people have developed multiple like coding systems. So across the hospitals, across institutions, right? Like you can imagine the same diseases might be coded in different ways, and that's why we want to do this alignment, right? So we want to use large language model to do this, and a very intuitive idea is you basically you take any new entity, right? You encounter in a knowledge graph, and you basically you put the whole ontology in your context window. You ask a language model which entity in the ontology is the most similar, the closest entity to what I have here, right? So the entity I have is called a query entity, and the ontology I have is called basically a corpus or like a target kind of set of entities, right? You want to find the particular target from a set of targets, right? And the problem here is you can't put the whole ontology into the context like a window, right? Basically because the ontology is too big. And what we did at that time is we did this two-step kind of pipeline, right? So first you use like a more traditional method to do a retrieval or to do like a pre-selection of the candidates, right? And then you use large language model to do re-ranking just based on the set of like pre-selected candidates, right? It's a pretty straightforward like a solution. And at that time, we just used like more like information retrieval methods like BM25 or some of the other like classic IR methods, right, to do the first step. And then we in the re-ranking, we just formulate the entities, the candidates entities, right, and in like a natural language, right, and then we ask a language model which one would be the best, right, the closest to my query. So okay, there's a slide missing, I think. So basically, for these two steps, we also design some techniques to improve each of them. So for the retriever, right, the problem is you want to get more of the relevant ones. You don't want to basically get rid of some of the potentially relevant target entities, because if you get rid of them, then in the re-ranker part, re-ranking step, there's no way to get them back, right? So the first step is you can get some like less relevant ones, but you don't want to get rid of the potential ones, right? So for that, we actually used the we leveraged the fact that the query entities we took were from a knowledge graph, right? So the knowledge graph has some in the knowledge graph, this query entity will have some neighbors, have some attributes, right? This will help us to basically generate a richer description of the query entity itself, right? So hopefully by enriching this query, right, doing something like a query expansion, right, we have more opportunities to get the potentially relevant entities in the first step, right? That is called a structure or attribute-based expansion, right? And then in the language model re-ranking part, what we found to be pretty important is we want to also, when we tell the language model, when we formulate the potential target entities, right, in a natural language, we try to also tell the language model how these target entities are organized in the existing ontology, right? So you basically, so you see you have a certain query like NFL, right, and you want to basically align it to a set of potential football leagues, right? And if you know what is the hierarchical structure among the existing football leagues, right? Some leagues belong to another, right? Some share some players or these things, right? So if you tell the language model this, basically let the language know about your ontology structure, then it actually helps the language model to select the more accurate one, right? So that is called a hierarchy context, right? You want to make the language model aware of those. So with those techniques, the method was evaluated on two kind of new data sets we constructed at that time, because you need some data sets that do share some entities, but in the same time, not too much overlapping entities. So at that time, we spent some effort to find this kind of sources, right? So you can really evaluate your alignment, but in the same time, the alignment is not too easy. So the high prompt is our proposed method, and we basically tried the 0 shot and 1 shot setting, because with more training, right, you can imagine some of the simpler methods actually can get quickly improve the results. Large language model actually gives more a boost in the 0 shot 1 shot settings. So we compared with some baselines. Basically, you can those baselines edit distance BM25. These are more like directly comparing the entity names, right? And you have this kind of separate or self-KG. These are embedding-based methods where you compute embeddings for the entities and compare the embedding distance, right? So all of these things you can also do like 0-shot or 1-shot like prediction, and our methods outperform those methods very, very like significantly. And we tried like to basically see like that attribute, so-called attribute enhance the retrieval or the structure in like the ontology structure enhance the re-ranking. Does they like do they help, right? They both provided some performance gain. And we also tried this. Our method actually is also like agnostic to the particular language models we use. At that time, we tried some different ones and showed like this our method can actually improve, give like bring improvement to different kinds of like language models. And we tried the and this improvement is actually more like obvious for the smaller, poorer models because of their lack of like knowledge, right? But that is actually a pretty important point, because like in medical, in real like healthcare like industry, right? You don't have a lot of like resources to always access the best language model. So if our method is able to bring more like improvements for the smaller models, even though the smaller models don't outperform the bigger models eventually, they still have some benefit in terms of cost, efficiency, and like IP kind of problems, right? So we did a lot of this kind of case studies with our like clinical physicians, like collaborators, right? To basically like understand how the model performs better, right? In one of the examples on the right, we can actually see like there's something called like a short stature, like obesity syndrome. This thing, if you ask a language model, even if you sometimes you ask a human to align it to put it onto the existing ontology, it's pretty hard. And it's hard because like you usually don't like the language model usually don't understand like this particular syndrome is actually also like a type of a disease, right? And if it doesn't understand that fact, it will put it more on the like a non-disease side, right? So that becomes a problem. That becomes like that leads to like a wrong answer, right? And actually that one, the short bow like syndrome, is actually some kind of analytical entity disease, and it's actually pretty different from the query, but they have a pretty similar name, right? So you need to basically understand this ontology structure to make the more like accurate prediction. So we did a lot of like case studies like that. This is like actually a continuing work of that, so I won't go into too much details. This is basically in a slightly different setting where we are not like aligning a KG to an ontology. Instead, we're trying to align like entities from the EHR record from the EHR data, right, patient record, to like a biomedical KG, right? Because like you can think about this, like if we want to reason about like a patient's like a status, we want to make like a predictions on the patient's risks, future risks, right? If we want to also make use of KG in the reasoning process, we will first need to like align the entities, right, from the EHR to the KG, right? And these are just examples. This I can't even like pronounce this like a disease name, but it's basically something very similar to that different name. So there's no way to like for us to understand this, right? And actually in this work, we show like how your language model can actually help you do that alignment. So I'll just go very briefly into like into the description of the method. So it's a very similar kind of idea to what we did in the high prompt work. It's basically 2 or 3 steps. Right? The first step is we generate concept representations. Right, this helps us to again filter out some of the more potential candidates, so we don't need to put all of the like entities in the knowledge graph into like one of the questions to a language model, right? Because that's too huge. And we use something called a BERT. It's basically a biomedical, like a BERT model trained with a lot of like online literature, biomedical literature, right? And that basically helps us generate better representations, embeddings for this kind of very unfamiliar entities, right? So then we use cosine similarity basically to do the filtering and ask ChatGPT what are the most similar entities, right, to one of the queries, to each of the queries. And we actually did that. So I don't want to introduce more about how we compute the embedding. I just want to see we have this kind of a two-stage prompt, right? The first stage is basically we ask language models multiple times to basically a simpler answer, right? For a simpler a question whether these two things are the same, right? And we basically ask the language model for more times to get more like a consistent answer, right? And we basically compute some kind of a ratio, right? How many times it says yes, right? And they use this as and then add a threshold that there to basically get the more confident ones. The next stage is a little bit more innovative, I would say. So we still ask a language model for multiple times, but we ask a language model to choose your answer from a set of potential answers. So the potential answers include exact match, subsetting, this disease is actually a subdisease of the other disease, right? And also basically null or not match, right? So it also has a possibility to directly see there's no match, right? So in this step, actually, we were able to do a few things. The first thing is we basically force the language model into really think about the relationships, not just answering a yes or no. So this is kind of forcing the language model to do a deeper reasoning. The second one is we also allow the language model to basically to say no. And that thing was not easy to do because if you don't provide the potential answer of no, language model will also try to make find some connections and try to really sometimes also hallucinate to basically get a seemingly better response, right? So you need to provide the specific opportunity to say no. So by doing this, I think I still probably skipped some of the important designs, but I think most of them are there. And the most important thing is being able to say no and also try to force language model to think deeper about the relation. So we compared with some baselines and again, computing accuracy wise, the performance looks much better. And also some case studies with the collaborators and some of the smile face basically indicates the things we found, the alignment we found actually is better than some of the baselines, right? And that basically is decided by our human collaborators, right? And the other one, the label sign basically says label wise, looking at the ground truth, we did better. So these are just some of the cases we were able to show in the paper. And there were more of this we used to compute the scores we also presented in the paper. So that would be about the integration. And I want to speed up a little bit when I talk about this construction completion, especially because these are others' work. So the idea is, right, you can basically right, ask language models, of course, using different strategies to ask, right? And then basically having the language model really do your entity extraction, entity alignment, and relation prediction, this kind of things, right? Even some multi-hop reasoning on your existing knowledge graph to create and insert more new knowledge, right? So there was a survey paper last year, also actually in the Triple Dub conference, right? So they actually imagined different ways of using large language models to complete a knowledge graph, right? So there are few data sets. These are just different data sets they tried to do the knowledge enrichment. Actually, I think the method they used is pretty similar to what Ling Hao just introduced in the third work, right? So basically design the so-called text-based prompts, right? To try to directly ask a large language model to construct, to extract some entities, some relations from each like a given piece of text, right? So they did some experiments in the paper and basically showed like I don't like I read the paper, didn't find a lot of like very exciting findings. So it basically says like your like the GPT-4 model performs better than ChatGPT. At that time, it's more like a 3.5 model. And that's because like GPT-4 has more knowledge, that kind of conclusions. And of course, I think they have more like they should have more like deeper ones. I probably somehow didn't find. The second work is about like also a little bit like further, I think beyond like what you directly like describe using text prompts. This one is about you actually they used several different like knowledge graph embedding based like relation triplet prediction methods, right? They somehow used like selected three kind of top three methods or the top three candidates generated by your like by a KG embedding methods, right? And then they ask the large language model about this to select the best from the three, right? Pretty similar to what we did in the past for the like the two steps like the process for like knowledge graph integration, right? The only difference is the task is different, and the first model, the first step, they use like knowledge graph embedding methods to do the candidate selection, right? And then they basically compare this so-called model. This like a KG like a KG generation based like a model, right, to do the relation prediction, compared with a lot of knowledge graph embedding methods, right, and showed that they got better performance in the prediction, in the like triplet like completion, knowledge completion kind of prediction, right? And this is a pretty like I think it's a pretty interesting one. It's based on like writing code, right? The ability of language models in writing code. So the argument they made was writing code, the task, the like a code as a type of data, code is pretty similar to like a knowledge graph. And why is that? Is because they can actually formulate the different structures, knowledge graph structures, constraints into code. Right? They think like a code also has a lot of like structures. So one of the idea here is this is a piece of text, and the text is like a less structured, less constraints. It's more like a free kind of a freestyle, right? And there is a corresponding like knowledge graph constructed from this piece of text. And actually, if you write about the triplets, you write about the knowledge in the graph, you can actually write it in a more kind of code style where you can define triplets. You can define triplet as a type of like an object, right? And then you can basically create a few objects that has a head, a relation, and a tail, right? So this way they make like a kind of analogy between code and the knowledge graph, right? And they think using code to describe knowledge graph is a very like a natural way. And then like knowledge graphs, we know like language models are pretty good at writing code, right? So the way like the thing they invented is called like a schema prompt, right? Which means like they design a way to automatically write code, and the code is written based on a given schema, the schema of a knowledge graph or the schema of the like a triplet that you need to formulate like following, right? You need to follow to formulate your like triplets. So and then they have this so-called like they use this so-called like schema prompt in their like in their prompts, right? And they ask a language, so they still like input a piece of text, and then the text is followed by this schema prompt, right? To ask the language model to basically follow this schema to extract to write code. And that piece of code, if the language model, the idea is if your language model write the code following your schema, then you can easily extract a triplet, or you can easily construct a knowledge graph based on that output, right? Because the schema is written in this way, right? You define your relation, you define your entity, define your like a triplet or specific types of entities, right? What the attributes entities could have, right? You write this all in like a type of a particular schema, right? And then if your language model follow the schema to write the output, then you can from the output you can easily construct a knowledge graph, right? So that is basically the idea, how you make a language model write code, and then you can generate your knowledge graph from the code, right? So there are some experiments, right, compared with some more like a vanilla prompt where you don't have this so-called schema prompts, right? And there are some examples they showed it's happen to be a kind of a medical scenario example again. So saying like a certain kind of a disease associated with brain damage was detected, and that disease is because the parent took some kind of treatments like during the pregnancy, right? So basically, there's some kind of logic underlying there. Like basically, you should the two things, the two kind of treatments the parent got, right, is causing like the disease of the infant, right? The basically the brain damage and also the CMW, the CWV, right? So this would be the correct one, but without the code, they show like it's like the vanilla prompt basically find pretty like wrong ones, right? So that is basically one of the methods I think is also like pretty interesting. So the final method here is about like how you can use language model, how you can fine tune a large language model to really like to make like a more like a knowledge graph completion task, right? And that paper, I read it more than one time, try to figure out like which part of the large language model they really like tuned to achieve this. I didn't find like a very like a concrete or very like a very much like a confident answer I can provide you now. So I can only tell you like what I understood, how I understood they are doing this. So and the way I would do it if it's me, right? So you have a knowledge graph, and the thing is they like they use a method to generate embeddings for the knowledge graph, right? And this I would understand it as like you use any kind of existing like a knowledge graph embedding methods, right? And you can train the embedding methods basically on your knowledge graph, and you get the embeddings. And what I know for sure, what they did is then they basically append this like knowledge, this like entity embedding and the relation embedding into the beginning of your like of this basically this piece of instruction, right? Basically, you did some like a kind of soft prompting. You put it to the beginning of the input, and then you ask the language model to make a prediction based on this combined like this additional tokens and your original tokens, right? And the language model will receive a response, will receive a loss, right? Basically, the loss is about whether the triplet is actually true or not, right? So you get a loss, and the loss is propagated back to the both the embedding model and that adapter. Basically, that adapter generates your like a embedding from your like from the embeddings produced by the like embedding model, right? So what I would do there is I will basically train that adapter, right, without really tuning the large language model. And what I know for sure, what they did is they pre-computed the structural embeddings, the like entity embedding and the relation embeddings, right? And they fixed that part when they do the fine tuning. But what I'm not sure about is whether did they only fine tune the large language model, or did they only fine tune the adapter, or they fine tune the adapter together with the large language model? And what I would do is I won't touch the large language model. I will only like fine tune the adapter. But I'm not sure what they did. So anyway, I think like right, like it doesn't make too much of difference like in terms of like understanding what they sort of doing, right, in the paper. Is the only part not sure about is whether large language model is really like trained. So they compared again with a lot of like knowledge graph like embedding completion, knowledge graph completion methods, and this method I think it showed like certain like improvements, not very like significant to my sense. But still, I think it's a very like a pretty interesting like attempt of using large language models to complete knowledge graphs. So finally, I want to also talk about some of our exploration on how we can use like multimodality foundation models, large vision language models, right? Particularly to improve the knowledge graph by using like imaging data, right? Images in the real world. So this is the first like a kind of work I want to introduce. So the idea is in real world, right? We have a lot of pictures, right? Can we actually get some of the common sense knowledge from the image, right? Like for example, the cups, right, will always be put on top of a table, right? And if there's water, the water will be inside the cups, right? This kind of like a common sense knowledge. So some limitations of existing methods is like we think like for example the knowledge format is a limitation. Like you always need this kind of triplet verb. Like in the triplet you always have a subject, a verb, an object, this kind of things, right? Existing methods when they consider like triplets from images. The second thing is you also have a pretty limited like vocabulary. Basically, the nouns you have, right, and the verbs you have are from like a predefined set, right? This is a limitation of existing work too. The other is like in terms of using languages to describe this like relations or describe the knowledge, right? The triplet, once you formulate your like knowledge into a triplet, it's again pretty limited. So what we want to do in this work is we want the so-called format-free knowledge. It's not necessarily can be written in a triplet, right? And also like open world like a vocabulary, so you can find your proper word to describe the thing, the entities, the relations, right? And we want it to actually to be pretty diverse. So this basically is the overall kind of things we try to do, right? From an image, which we want to identify regions that are like that are relevant to a relation, right? And we want to basically do some kind of prompting and ask the large vision language model, right, to output like a relation, right? And that relation hopefully is relevant to the to what the language the model find from the image, right? So we have some like technical designs. The first is there are lots of like low quality data and low quality images and also like low quality like captions or whatever like textual output, right? So what we try to do there is we design something like a TF-IDF to basically find the more like the more frequent ones, right? But also in the same time not so frequent like across all of the images, right? So you basically want to find more of the robust and also like unique facts from each image, right? So we use that to weight the data, to weight the training data, basically reduce the like possibilities of like using the low quality data. The second thing is so-called like a second more important thing is so-called like a relation, like a free open world kind of relational region detector. So the idea is like in the data set we use, we only have like the bounding boxes for the specific objects, right? Not really for relations, but we want to in this project, right? We want to find the relations, right? So what we did there is pretty simple. Like we basically use the combinations of each pair of like entities, each pair of objects, right? And we use some kind of so-called like knowledge supervision. So basically the idea is we use some like existing knowledge graph to basically filter out some of the less likely combinations, right? So you don't get like a very large number of like combinations, right? So the second thing is called like a format-free visual knowledge generator, and the idea is we basically after we have the image and we use the like we use the masks to highlight the relational region, right? And then we use the like a vision language model to generate a text, a piece of text, right? And we use the image caption to supervise that text, right? So in this way, we make the model being able to generate a piece of like text that describes the relational knowledge, right, from the image, right? So this is like a so in this way, what the model does is really to generate a piece of text instead of making like a classification or choosing like one of the relations from a predefined like a set of relations, right? So this makes the results really like format free. So this would be the whole framework. Kind of we have an image kind of encoder, right, to take the input of a image and generate like the bounding boxes, right? The bounding boxes again are supervised by our like relational like regions, right? And then use this like image plus the masked like image of the bounding box, right? We then generate like we try to generate the relation, and that relation would be supervised by a piece of like a free text, right? So in the end, we're able to generate the so-called like a open visual knowledge. So of course, there's a lot of like further details ignored in the talk, but they can all be found in the paper. We compared with a lot of like baselines using like different kinds of scene graph generation or like relational captioning, dense relational captioning, right? So compared with these models, we get like we used a few like commonly used metrics and also designed a few like metrics of our own to highlight like the different perspectives of the knowledge we generate, right? So there's also this so-called like a parametric or non-parametric knowledge. So non-parametric knowledge is more like the knowledge that people put in a knowledge graph, like ConceptNet or any kind of like a free-based, this kind of more traditional knowledge graph, right? There is also the so-called like parametric knowledge is more like this knowledge is always associated with a model, like the recent comic model or the recent or large language model, right? Basically, you can always ask the model to generate knowledge, right? So this knowledge are called like a parametric knowledge. It's bounded, this knowledge is bounded to a model, right? So we compared with different kinds of like knowledge graph, right? Like the knowledge we extracted from the image with knowledge inside this kind of non-parametric or parametric knowledge graph, right? And basically to show we actually generate compared with a non-parametric knowledge graph, right? The things we generated are much more like a freestyle, much more like a human friendly, right? And there are like some parametric knowledge, both our model and the like some of the existing model can generate similar styles of like knowledge, right? And there are some knowledge only our method is able to generate because we take the input of the images, right? Not like directly prompting the model, right? So some other like experiments basically to show the several like the benefits brought by several of the major like model designs. Okay, so some interesting case studies as well. So you can see like we highlighted some of the terms which are either like new entities we found from the image, which are not there like in any of the existing like knowledge graph embedding models, knowledge graph like knowledge graph models or existing knowledge graphs, right? And there are also the way we use to describe this like relations, right? Like the wood box full of different sizes of oranges, like full of this kind of word is never used in existing like knowledge graph, right? It's more like a diverse, the open world kind of vocabulary, right? So do I have more time or like does Evgeny want to start now? 10 more minutes, okay. Then I will go very briefly about this final work, and I will leave a few minutes for the questions. So of course, like again, nowadays we work a lot on health data. We care about like real world healthcare problems. So like how can this kind of large like a multimodality model, like a multimodality knowledge extraction framework help like health related like problems, right? So there's a lot of like medical imagings and different kinds of like textbooks, like a clinical kind of guidelines, right? Different kind of things that you always have different kinds of pictures in this like corpus or this kind of texts, right? So one thing we wanted to do was can we use a model to basically like how can we align the like imaging model with like the text, right? So this step is actually before we can actually extract like medical entities from medical images, right? The first step is how can we align like medical imaging or any imaging model with like the textual space, right? Once we can do that alignment, then we can design similar kinds of like prompts, right? Visual prompts, right? Like I introduced in the previous work, right? To get more like relations, more like medical like knowledge from the like multimodality data, right? So this work is about align the model, not yet about the knowledge extraction. So the problem is, right, we want to, for example, we have a lot of like CT images, right, in the patient data. And also there, we can also have like a radiologist's report about like after they read this CT images, right? So naturally, this kind of image and the paired report would become like ideal data for us to train, like to really fine-tune a large vision language model to align the vision, the visual and the textual like modalities, right? But the problem is this is not good enough, because when you have an image, when you have a CT image and the corresponding report, you don't. Oh, I see my computer dead. Oh, the computer is okay. I think I can still like just briefly introduce that work even without the slides. So the problem is you only have the image and the corresponding report, but the report doesn't have like the corresponding kind of bounding boxes, or the like the report also doesn't have like this alignment between the like the more particular region where the disease is actually like happening, right, in the image. So because of that, if you directly only have an image and the whole text like describing the image, you still don't have the like fine-grained enough data to train to basically like align your like text space and the image space, right? So in that work, what we did is we try to use like a large language model or large like vision language model to help us like generate some of the fine-tuning data that has the more fine-grained alignment between the images and the texts, right? So-called more fine-grained alignment is if we the like specifically is we want to generate an image and also the corresponding bounding boxes where you actually identify the like the lesion or the like inflammations or this kind of disease characteristics, right, in the image, right? So you know like each text, each piece of sentences, what each piece of the sentences in your medical report is describing, right? So we want to generate more of this kind of data to help us understand like to help us really fine-tune a large vision model, right? Not like a language vision model. So we did this in 3 steps. The first step is we ask a clinician to generate a few examples of this more like fine-grained, like annotated data, image and text pairs, right? And then we use these pairs. We basically input this kind of pairs to the to a large vision model. At that time, we used like a GPT-4V. And we basically ask the GPT-4V model to follow the examples to generate more of this kind of fine-grained like pairs, right? And this is a step, right? We use the GPT model to generate more of the pairs. But then the GPT generated pairs, right, may not be like of a high quality. So we have a second step of a selection. So basically, we try to select the high quality data from the GPT-4V generated data, right? And what we did there is, again, we can ask the clinicians to help us do the selection. But again, if you use GPT model to generate a lot of this kind of data, and then ask the clinicians to even select like the better ones from this data, is still pretty hard, right? So what we did there is we only ask them to select like 100 or so, like a very good quality like examples, and then we further trained a model to basically classify the good examples from the bad ones. So in that way, if we can train a pretty good classifier, then we use GPT-4 to generate millions of like new pairs, right? And we use this classification model to choose the higher quality ones. Then we get a lot of like free training data for the model, right? So that is exactly what we did. So the last step is just to use this a lot of like free training data to really train the alignment model, right? So we use this model we conduct a lot of like different kinds of like tasks to evaluate the model. And in many of the cases, we get better performance. And there are some blanks in the table because we focused on the kind of open world like a kind of scenario where the question like the answers are evaluated more in the like open world kind of setting, right? So some of the model we were only able to take the like references scores they reported in their paper, and some data sets they didn't do the experiments, so we weren't able to like really reproduce them, and because it also it's complicated and also take a lot of time. So what we compared mainly, we implemented these models. It's more like our ablations, our like different variants, and we did the experiments on that to show basically how our model is able to reach a better alignment and perform better in the like a medical imaging based like a medical QA, right? So yeah, that kind of ends my discussion, and I think we are about the time, right? Yeah, thank you. Any questions are welcome too.
Hi, Virginie, can you hear us?
Yeah, well, we bring up
Yes,
our
yes, I can hear you.
speaker.
Yes. Yep,
Any questions you have, we were happy to answer.
I will join just
Can you
in
try
2-3
to
minutes.
speak
Yeah.
something to see whether we can hear you?
I can hear you. Can you hear me? Hello, can you hear me? Hello, I can hear you. Can you hear me? Hello, hello.
Yeah, I think we
Can you
need
hear
to
me?
mute some of the.
Yeah.
I'll be online just in 2 minutes. Yeah.
I think we cannot hear you.
I think we should disconnect the mic. That's how to remove that. We don't want to mute this.
Hello, hello.
Wait a second, we need some help from.
Yeah, any questions? Yeah, thank you.
Yes, I just have a question about the semantic gap. You know, there is a semantic gap from the LLMs and the KG.
Right.
What do you think you can?
Yeah, that's a very good question. We got this question like from every reviewer, or at least from one of the reviewers of every paper we submit, right? So there are things we did was like because we are extracting knowledge from literature, right, or from some multimodality data. So what we try the first thing is we always want to extract knowledge that is consistent with the input.
Meeting this.
So we hope to reduce so we just use large model as like a knowledge formatter, right? So you take knowledge from literature and you just format it as it was in the literature. So we try to limit the language model from like hallucinate things, from like from just putting its own knowledge in there. And one particular technique we can use to do this is we repeatedly do the same task for multiple times, right? And we only keep the consistent ones, because that is if your language model hallucinate or if it generates some knowledge not really in the text, it will get different results, right? And we only take the consistent one. That is like one thing we always try to do. basically.
Yes, I can hear you. Can you hear me? Can you hear me? Hello? You can hear me, yes? You can hear me. It works. Okay, okay. Just give me 1 minute. I'll connect laptop to the power and I'll be with you. Okay. Okay, just 1 sec. I'm starting presentation and you'll see me in a moment here. Just 1 second. Can you see my screen? Can you see my screen? I cannot hear you. Maybe you cannot. If you can see my screen, make some signal. For some reasons I cannot hear you, but I believe maybe you can hear me. Or okay, I think you can see my screen. Yes. Okay, I can see my screen on your screen. And can you just make a signal whether you can hear me, and then we'll start if you can hear me. Chat. Okay, yes, I see the chat. Okay, thanks a lot. Yes. Okay, so let me then start. Right. I will be talking about applications and the synergizing between knowledge graphs and large language model systems. So what I will tell you, I will first start with an intro to the GenAI reality in large companies today. And from this reality of large companies today, using Bosch as an example, I will go into the topic of the most common use of large language models that motivates actually knowledge graph to be used, so in the RAG, and then we will be talking about graph RAG and RAG for graph knowledge graphs for RAG and various applications surrounding them. Let me start with what I would say a pretty much expected pattern which you can see in a large company. So like Bosch has about 430,000 people and working in different sectors and manufacturing services. And as many large companies, Bosch does quite a bit of AI related topics. And that was all going in the usual way for quite many years, as many companies, so deep learning and very with other topics were top on the radar. And just recently, as you all know, we witnessed this new big hurricane coming while we are moving our lawn with very comfortable AI. Then this massive new Gen AI came and actually made quite a bit of changes in the whole in this whole picture. So when this new hurricane, this new reality arrived, large language models arrived, then in Bosch, as in number of companies, I will say later, the situation was that at the response, various units, various plants, various divisions of Bosch started to investigate what are the use cases, where these large language models can help. So that since Bosch has many plants, like 200 plants and many different offices, so they were investigating use cases, looking at different large language models and looking how they can help developing solutions and infrastructure. That was going for a while until there was also an attempt to kind of consolidate together various GenAI initiatives across the company to consolidate use cases, models, and solutions and infrastructure, and to see how they could be applied across various business units inside the company. And so this led to defining routines, defining ways on how to onboard GenAI or large language model centered use cases and applications. And so there were, for example, some four steps developed and communicated how one can go with that. There was like collecting use cases, clustering, technical feasibility studies, legality understanding of whether it could be used language models for this topic. So moreover, the use cases has been grouped, clustered, aggregated across four essentially large groups that are either related to NLP search summarization or chat bots, voice bots, so then content creation and things like engineering and software development. So in these four directions, majority of the cases that were coming across Bosch could be summarized, and we're talking about a lot of cases in each of them. Also as a result of this more centralized approach, there were also implemented standardization and governance routines on how to onboard tooling and how to steer this tooling onboarded across GenAI, because obviously there is, as you know, there is a whole explosion of LLM-centered tooling frameworks and God knows what. And the idea was to put it in somewhat reasonable and corridor to make sure that there is not much on anarchy, and was work on onboarding tool, tech stack, providing the technical stack, and then assisting with development, and also research was isolated as one of the important critical aspects related to the GenAI. So why I'm telling you that? Because this is not, as I said, it's not something just Bosch is very unique in this way. My colleagues from Siemens, Infineon, Volkswagen, other large companies, they I saw their presentations, was in touch with them. They communicate pretty much similar pattern that is happening there. This is the reality of large companies. GenAI came, large language models came, was a hurricane, and then first this like an anarchy of testing and exploring and looking at what can it be done, and then some approaches to bring it together, consolidate, and try to steer this from a centralized way. So yeah, so that was also done in Bosch, and so in those GenAI related initiatives. So there were things like this in-house ChatGPT and another systems and services and another approaches have been provided. Bosch also been investing in some large language model related companies and making alliances with hyperscalers like Microsoft. So that was a lot done in this buy versus build thing, because that was another thing. It's a new area, and how to deal with that, what to build, what to buy from the external market for companies who are not companies that are not specifically software oriented, in the sense that the companies whose main business is not to provide software solutions like Microsoft would. So they were also doing this a lot of analysis. So that was, this is, when we're talking about applications of large language models and knowledge graphs, it's very important to understand on where those applications are coming from and how exactly companies came to these applications, what was the trajectory. And this is the trajectory. This is something which is not 20, 30, 40 years old. This is something that is literally a couple of years. The LLM hurricane came. Now, what was observed is that in majority of cases, say 80+% of the cases, what is really needed and what can really solve the problems is solutions related to information retrieval. And RAG, so this retrieval augmented generation, one could see that it is in the core of solutions for vast majority of use cases, not for all, but for vast majority of them. The issue, Bosch, Siemens, other companies witnesses that this could be described that if the company knew what it really knows, then it could improve and could function much better, can do better cost saving, could produce better products. And what it means, if the company knew, if Bosch or Siemens knew what it knows, it means that there is such an ocean of information scattered across, and it was observed that actually large language models can provide a really unique way of getting access to this data, making it actionable, and create value of that data. And data has been in the companies hidden in manufacturing environments, in ERP systems, in many different places. And actually, at the very beginning, simple and cheap solutions were doing some great results, surprisingly good results. So some base RAG where you take data, map it into the vector spaces, and then do retrieval and then do this LLM with use LLM in that way. Just to give you a little bit of this reconciliation of what this RAG is, to understand and to then see why this approach didn't last for very long, and there was an understanding that we'll need to go way beyond the traditional RAG. And let's observe that RAG works in the following way. So the data to which you'd like to get access, and as I said, it's 80% plus cases, when you have this data, this hidden jewelry, these hidden gems gems hidden in the in this data. So what do, you chunk the data, you embed the data in store these chunks, embed them and store them in a vector database. Then whenever the query comes, you match the query, also you vectorize it, embed it, you match it to the to the data. You see which chunks are the closest to the query, and you retrieve those top key chunks, and then you use them as the prompt to communicate to LLM and then to get the response. So amazing. As I said, pretty simple and cheap solution in the sense that it doesn't require some rocket science technology to do this type of RAG, and apparently it already goes into the direction of being a good solution for 80+% of the cases. Of course, this was a simple base RAG, and as you witness in the last couple of years, there was also an explosion of different variations, all the kind of different beasts that stem from RAG and improve it in various directions. In particular, nowadays, the one which is heavily discussed is the agentic RAG. So this is the RAG that is considered today is like this, the most advanced RAG, and this RAG is working in a way that it's not this simple vectorization and the retrieval thing. So we're talking about multiple agents that are specializing in different directions on how they can perform retrieval, how they can, maybe some agents specializing on web search, some agents specializing on the retrieval of data in databases, some are on some Gmail or some other things, and then bringing this retrieve data, and then is retrieval things, what is retrieved orchestrated and then sent back to the user via the LLM. But what came pretty fast apparent is that the vector-oriented RAG suffers from so the LLMs per se, they suffer from hallucination, and the RAG, it does solve partially this problem of hallucinating by enforcing this advanced prompting with the help of the retrieval. At the same time, still the approach has similar problems, has quite a lot of problems in terms of hallucination, but moreover, there are also limitations in what actually the basic RAG is capable of doing. For example, it was pretty fast. People realized that vector similarity is not necessarily the relevance. So when you have your query, you map it to the data in the vector similarity way. It doesn't mean that you will get good context that you retrieve. These black box operations, they focus on the fragments of data, so you can ask all LTP queries rather than all up queries, aggregations across data, and a number of things were either impossible with traditional RAG or the results unsatisfactory. So RAG was a solution, but the solution which only partially becomes satisfactory. Moreover, a solution that was really good at the very beginning to see, wow, such an amazing results can be done with the RAG. But when you look closer, when you look further, when you look at multi-hop queries, you immediately realize that this is not helping you that much. Graphs came as the rescue. And knowledge graphs came as the rescue in that. And I will now tell you a little bit on how and why. Let's look into the graphs. Actually, what I can say is that graphs, they have an interesting destiny. They came into the rescue in information retrieval already quite some time ago. So this is not the first time when graphs enter in the area where users focus on retrieval-oriented tasks. And as I mentioned, we're talking about 80+% of the use cases that are focusing on retrieval at the end. We're talking about if the company knew what it really knows, is getting the knowledge, the company's knowledge, and making the value out of it. So it is heavily retrieval oriented, and we witnessed this already in end of 90s when in the web search, in the retrieval from the web, graph-oriented methods like PageRank came into the rescue and boosted the whole industry and really revolutionized the quality of response when the graph-oriented methods were introduced. Really went up heavily. Then actually in the same, so the next step in this journey of the graph at the rescue was that knowledge graphs came, and Google after the PageRank also introduced coined the knowledge graph term, and again that was the next level of the retrieval where the answers could be presented in this beautiful way. So now, if you, for example, take a look at the Google keynote of 24, you can see that we're still considering with the graph journey. So the next stop in that, as according to also this, if you look at this Google time trajectory, is this graph already introduced, this knowledge graph introduced as the way that you can bring it into the LLM context, that when you do, say, travel planning to Miami, and then the system can look at data related to you, see your travel experiences, your preferences, and so on, and then observe this graph that Google possesses and can help you with finding the place, recommending some booking options and things like that. So that's the next level where LLMs plus graphs came together. So that could be seen as this pathway. So in the first, like this, this part of the Google story where we came through the page rank into the knowledge graphs, and now it went further when the LLMs and the graph rack is coming. This is the new era of the graphs, and again, what is really exciting to see here is that graphs, as the graph themselves, they come into the rescue one more time again. So that's somewhat, when we get to the data, graphs are really we're really destined to them. And when we're talking about this graph graph intrusion into the rack area, we are talking about graphs that can be used to as the way to aggregate data, like the superset of data, to put structured, semi-structured data together. Plus, they can use the way also to be on top of the vectors and on top of the embeddings, because then the embeddings can also be not just text-oriented embeddings, but they can also leverage from the graph structure, and they can already be way more advanced. So in the graph rack, we're talking about the graphs that come into the game in various places, starting from the data in encoding into this and influencing the vector thing. In the essence, the graph rack itself, when we talk about that, there is, say, no specific modality of how the graphs should come into the game. There are many ways how graphs can be introduced, and they form this graph rack approach. So in principle, again, there is no like a massive magic with this graph rack. It is a rack where the retrieval come with some form of a graph. Whether it's like this entity graph interconnecting data, or it may be the graph that organizes the chunks of text, lexical graphs, and some other types of graph that can come into the game and boost the retrieval. There is no universal standard, so in many ways, those are different types of the graph rack. And for that, this actually boosted quite also a lot of the industry. So the graph databases were already on the rise, and that gave them an extra an extra power, an extra boost further, because now the graph databases could become this universal, also the universal data format and the universal storage where data can be used. This data can be used. Just one second. Yes. Okay. So so this So this is another thing. So this also influenced quite a bit. This graph rack put this another influence into the industry of data stores. Yeah. So let me give you a couple of canonical examples of how of graph rack. In particular, one comes from Neo4j. Neo4j is the company that is offering graph database, plus now it offers graph rack, and it offers also agentic solutions related to graph rack, because the dimension. So the agentic rack is the next, is like the, in some sense, the latest generation of rack, I'm not focusing much on the agentic part here, but essentially those who do offer rack solutions, they ultimately go into the direction. Neo4j, in connection to Google, they have these ways of offering powerful agentic rack solutions. So that's this is the architecture. Again, as you would probably expect, when the user interacting with data, where the data is not only the vector, not only the vectors, but also the graphs participate as data integration and also the embedded the vector spaces. So graphs, knowledge graphs give enormous flexibility on how to control the retrieval process and how to make it much more precise, much more clear, this contextualization. And instead of simple vector search, one can explicitly traverse paths in the graph whenever the query comes. One can do not only this looking at the neighbors in whatever distance measures, but also explore neighbors, do this number of hops starting from a specific node in the graph in order to retrieve the context. So it came also a lot with the ease of development and for applications we need high quality answers. And large providers of these graph backends like Neo4j, they have the whole library, the whole bunch of libraries how you can that you can rely upon in order to boost your retrieval. Then a big milestone in this marriage of graphs and retrieval and RAG was the Microsoft Graph RAG, where the observation was that global queries are not really working. In the RAG, you can ask for, give me some people who are doing something and this you can ask again the data or for some processes and stuff, but one cannot really ask like top 10 topics in the data and other aggregate information, because by construction RAG is done in such a way that it is local, it is localized, and it is only focusing on a bunch of chunks rather than on the global picture. And Microsoft Graph RAG is the way to address that. The idea is to organize data in a bunch of communities, and then to, whenever you ask an aggregate query across data, you aggregate across these communities and get this, for example, what do these reports talk about? If you have a bunch of reports, then the Graph RAG can really look for the topics, the most common topics across all documents. And if you ask just baseline standard RAG, the only thing it can do, it can just give you a handful of topics that are in the data, but it cannot really give you the 10 most important topics across the whole documents. And this is the thing that the Graph RAG can offer by interconnecting documents in these collections of documents, grouping them in the communities, and then whenever you ask this summary across the entire corpora, then the summary can be studied from community, then communities and communities propagate it up, and then compute it. So then also there were a number of studies that show how the accuracy goes up dramatically from Microsoft, from linked from Facebook. I think this work, it was from Facebook and other authors. Right. So oh, sorry. So okay, where's my last slide? Okay. So let me then come back to the topic to where I started. Yes, just a sec. Okay. Yes. Part 4. Just a sec. Let me come back to where I started and sum up. So what I wanted to share with you is that large language models came into companies as the hurricane, a new reality, and that came with enormous amount of opportunities, and the company started to embark on those opportunities. And the first thing that was done was to understand the impact of that, understand where the LLMs can be applied, and what economic effect they can do. From this chaotic approaches across individual units, it came to more the centralized approach where things got crystallized that retrieval is the big part of the use cases, and it can be 80+%, depends on the company, depends on the specialization of the company. And then it became pretty fast obvious that the classic RAG has severe limitations and has to be boosted, and the graph RAG happen to be graphs happen to come to the rescue here. Again, as I said, they're coming to the rescue in the retrieval already for quite some time, and they're here again. And so that's knowledge graphs plus a way to do high quality retrieval and to enable in companies like Bosch and others to get the value out of the data and to reduce costs, to improve processes and other things. So that's this is where the graphs plus LLMs, knowledge graphs and LLMs, they have now a very important niche. Yeah, that would conclude my talk. Thank you. Okay, for some reasons I cannot hear you again, but I can read. So if anyone is having a query, question or something, yeah. Okay. Yes, thank you so much. Yeah.